Alright, continuing the series with this later part of the calculus manual. We're looking at volumes by disks and washers today. Again, special thanks to Sue Schwartz and all this cool technology that we've been using. So let's go ahead and get started. Let's jump right into it. First of all, whoops, looks like we misspelled something here. Strategies that we're looking for. As you go through this process today, it's going to be helpful if you look back at this idea. So if you need to take a second, write this down. It's not in the manual, but it might be helpful. You want to ask yourself, is the axis of rotation attached to the bounded area? That's the thing that we're talking about, to the bounded area. You got to ask that first, because that's going to determine how you set up a template to evaluate that volume. Or is there empty space in the middle? That would be the other option. What is my direction of integration? Is it going to be dy or dx? Which one of those are we going to be using? Because that determines a lot of other things that we do with the variable expressions that we plug in. We also need to find the pieces. That's kind of our last step. What's those radii if we need them, and what are our limits of integration? So let's go ahead and jump right into the first one. If you need to, go ahead and pause it. Otherwise, we're going. So the first thing, our function is y equals 2x. So I'm going to go ahead and draw that on my graph here. Y equals 2x looks like a line about like that. I know that this is going to go to x equals 3, which means that on the y-axis I'm actually at 6. So if I'm right here at x equals 3, then on the y-axis I'm at y equals 6. And this line here is y equals 2x. The area that I'm interested in integrating here is going to be this part that I shade in. It's bounded by these lines, y equals 0, x equals 3, and y equals 2x. So I'm going to be rotating this around multiple different pieces. Let's go ahead and start with the first one. It shows that I want to rotate around the x-axis. If I'm going to rotate around the x-axis, that means that I'll be traveling perpendicular to that direction. So let's go ahead and go through our protocol. First of all, is it attached? Well, here's my axis of rotation, and the bounded area is attached the entire time. So yes, that means that I don't have to subtract an empty space in the middle. That means that I'm simply going to be looking at the template pi times big R squared. And I got to figure out what A and B are. Now the second question is it dy or is it dx? I'm moving in the direction of x, so it's going to be dx here. That also determines that these boundaries are in terms of x, as well as my function r. So now I just need to translate everything and figure out what each piece is going to be, what value it's going to be. So if I look at the first one, the lower boundary starts at 0. So I'm going to have the integral from 0 to, then I end at 3. And I still have the pi here. My volume is equal to all of this. Then I have my function dx, and I know it's going to be radius squared. I just got to figure out what that big radius is. Well, that radius is the distance between the two lines here. So I'm going to color that in red. I'm looking for that distance. And anytime I need to find the length between two lines, it's usually the more positive value minus the negative value, or even minus the lower one, the big minus small, top minus bottom, all those kind of things. So r is equal to that top line, 2x, minus the bottom line. So the first line is y equals 2x, and the second one is y equals 0. So that length is just 2x. So my radius, my big radius, is 2x. And for the little radius, I don't really need it. So I'm just going to cross that out. So in here we have 2x squared. Now I'm going to go ahead and evaluate this one just to get in the practice of doing the antiderivatives and see how it works out. So my volume is going to be equal to pi times, well, inside here this is really 4x squared, because when I square quantity I got to square both pieces with 2 squared and x squared. So I have pi times, then we got 4x squared, and the antiderivative of 4x squared is 4x cubed over 3. We're going to be evaluating that from 0 to 3. And I notice that when I have this 0 here, if I plug that in, it's not going to give me anything for the second part of this evaluation. So I just really need to plug in a 3. 4 times 3 cubed over 3. We're going to multiply that by pi. So 3 cubed is 27. Divided by 3 is 9. And then times 4 is 36. So this equals 36 pi. So there's our volume, 36 pi. Alright, let's keep going. This one's slightly different, but let's go ahead and get ourselves set up here so we can see what's going on. If we're rotating around the line y equals 6, we have a similar rotation, but some of the answers to our questions are going to change. So we still have the same pattern, same bounded area. Go ahead and shade that in. But now the difference is this orange area here is actually going to wind up being not used at all, because I'm rotating around the line y equals 6. Now I'm doing a vertical rotation here. My disks are aligned vertically, so that means I still have the dx, and from x equals a to x equals b, but something changes significantly on the inside. Because this area here is not attached to the axis of rotation. That means that I got to subtract that orange. So I got to figure out my big R and little r. So let's start with big R. That means, let me step back here a second. That means that we're going to have pi on the outside, just like normal, constant pi for our volume. We're going to have a big R squared minus a little r squared. And this little r is that inside piece. And the big R is kind of different. It's not just from the blue area, it's the whole. It's from the axis of rotation all the way down to that outer edge. It's this radius here, which actually happens to be constant in this example. And then for the other one, let's do that in brown. That's going to be our little r on the inside. So let's start with this. Our big R is going to be 6, that axis, minus that outer edge, which is just 0. So it just equals 6. That's easy enough. Then for the little r, which is on the inside, we'll do that in brown. Little r is going to be that 6 again, minus, and then we have this edge here, is that line, y equals 2x. So that's going to be 6 minus 2x. So now when we set this up, we're going to have each of those squared. So volume equals the integral. Oh, and by the way, our boundaries are still the same from 0 to 3. 0 to 3. We have pi on the outside. We've got the big R squared minus the little r squared. So that's going to be 6 squared minus, then the quantity 6 minus 2x squared. I'm going to go ahead and leave it like that. I'm going to focus mostly on setting up these problems today because you guys can use a calculator for the most part. And we need to focus more on the hard stuff, which is really the setup. This is a dx, by the way. Alright, let's do the next one. Okay, this time we're rotating around the line y equals 8. Let's go to move this up, give ourselves a little bit better view. So let's get our setup with our axes so we can see what's going on. still have that same y equals 2x kind of growth. I'm giving myself a little bit more space because now I have to go up as high as 8. That's my line y equals 8. We still have this bounded area here. So I have these pieces. We have x equals 3, x equals 0. We still have the same bounded region here. But now we're going to be taking out this. Whoops, I want to make that orange. So we got to figure out, how do I take that orange piece out? Well, going through our questions again, is it attached? No. Therefore, we're going to have our volume equal to, from A to B, pi, but this time it's big R squared minus little r squared. So we need to figure out what this big R and little r is. But before I get too far ahead of myself, let's ask my other question. What direction am I going in? Am I going the x direction or the y direction? Well, if I'm rotating around this line, y equals 8, then I know that I'm traveling perpendicular to that. So I'm going in the x direction. Again, dx. So this is x equals a, x equals b. Those are staying the same from before. So the volume equals pi times, well, a to b is 0 to 3. We need to figure out big R and little r. Big R, again, is a constant because the axis and this outer edge down here are parallel. Those two lines are parallel. So there's no change in the distance between them. So big R is equal to 8 minus 0, which is just 8. And little r, do that one in brown again, is now, it starts at 8 but goes all the way down to that line, which is 2x. So little r is 8 minus 2x, because it goes from this line up here to this line down here. So we have 8 minus 2x, and big R is 8. Let's get our setup finished then. So this is going to be 8 squared minus, and then we have the quantity 8 minus 2x squared dx. And then the volume is just equal to that. So if I were to simplify it at all, I would have pi times the integral from 0 to 3 of 64 minus, and then we have in here 8 minus 2x quantity squared all dx. There we go. Let's do another one.